along the street. And we extended the idea by considering two measurements, one after the other, so that we can measure the position of the bus and also the velocity of the bus by considering the difference in time that takes for the bus to go from position x1 to position x2. One may argue that this measurement is actually not too precise, because when the transmitter drops the tennis ball, we are referring to the left part of the figure, so to position x1, and the tennis ball hits the bus, there is an exchange of energy and momentum, because this is a collision between two bodies. So the bus may acquire or lose momentum depending on the characteristics of the collision. So the momentum of the bus after the collision is not exactly the momentum that would be present if no collision had occurred. So what we actually measure is the velocity after the second measurement. We possess the velocity of the bus after being perturbed by the first collision at position x1. And this is undoubtedly true. The collision with the tennis ball does perturb the motion of the bus. So it is perturbing the real thing that we are measuring. And as we shall see, it is impossible to measure a dynamic quantity without interacting with the object that we want to measure. So it is impossible not to perturb the motion. But there is an easy way out, that the mass of the tennis ball is so small with respect to the mass of the bus that the perturbation is negligible. Or maybe the perturbation is undetectable. It is below the limit of sensitivity of the measuring equipment. So there is a perturbation, but we simply can neglect it, okay? Now we go to another measurement. We want to measure the dynamics of a tennis ball using tennis balls. Okay, so we may refer to the lower part of the figure, in which there is a tennis ball coming from the left. So instead of the bus, we have a tennis ball. And the positions of the transmitter and receiver are reversed, but it doesn't really matter, okay? The conceptual thing is just the same, okay? So there is a tennis ball arriving from the left, and at position x1 there is a transmitter that launches every second a tennis ball equal to the tennis ball that is being measured, okay? So the second tennis ball is not visible in the figure, but assume it is just the same as the one that we want to measure. Obviously, the interaction of the tennis ball to be measured with the tennis ball that is ejected by the transmitter is not negligible. So we have a substantial deviation of the trajectory of the tennis ball to be measured. So assume that, as you may see in the figure, the tennis ball to be measured is deflected upwards. Okay. At some point, it will cross position x2, and then there will be another tennis ball coming in that is ejected by the second transmitter. And the second transmitter will also add another perturbation to the trajectory, so the tennis ball that is being measured will again be deflected. Assume that it is also deflected upwards. Okay, so what can we say about this measurement? Okay, the only thing that we can say is, well, we have the information that the object to be measured, the tennis ball that we want to measure, was at position x1 at time t1. And also then we have the information that it was at position x2 at time t2. So there is nothing against stating that the velocity of the tennis ball in between the two measurements can be calculated by taking the difference x2 minus x1 divided by t2 minus t1. This is something that we can still do, okay? So we have some information about the velocity of the tennis ball in between the two measurements, because we assume that in between the two measurements, nothing else has perturbed the motion of the tennis ball. However, from this measurement, we cannot deduce much about the dynamics of the tennis ball before the first measurement, okay? Because that was perturbed. But also, we cannot do anything useful about the motion of the tennis ball after the second measurement, because again, we have perturbed the motion, okay? So the perturbation is becoming essential, okay? We can say very little about the dynamics of this tennis ball. At most, we can say something about what happened in between the two measurements, okay? You may think that there is an easy way out. So a possible easy way out is, well, we know how to calculate exactly the result of the collision between two bodies, okay? This is a calculation that in classical mechanics is easily done, assuming that one knows the potential energy of the interaction between the two particles, okay? So we may say, when we want to calculate the deflection produced by the collision at x1, that is with the first tennis ball ejected by the transmitter, we simply calculate this using classical mechanics. But in order to do so, we should know exactly the initial condition of the motion, not only of the tennis ball that is ejected by the transmitter, but also the tennis ball that we want to measure, okay? So it is like a recursive reasoning back to infinity, okay? In order to calculate the collision, we must know the initial conditions, but in order to know these initial conditions, we must measure them, okay? So still more measurements, okay? So the difficulty is not removed by the idea that we could use just the calculation of a collision from classical mechanics. Another possible way out that is more sensible is if we want to measure the dynamics of a tennis ball, we simply take particles that are much, much smaller than a tennis ball. Like we did earlier with the bus against the tennis ball, okay? The two masses are so different that the perturbation induced by the collision can be neglected. So when we want to measure the dynamics of the tennis ball, we may use electrons. We eject electrons instead of ejecting tennis balls. And everything becomes easy because the mass of the electron is so small with respect to that of the tennis ball that the perturbation due to the interaction can again be neglected. Okay? So it looks like we are okay, but of course we are not. Because what if we wanted to measure the dynamics of electrons? And unfortunately, there is nothing that we can do because nature is not so kind to us. So nature does not provide us with particles that are so small with respect to electrons that we could measure easily the dynamics of the electrons. Okay, electrons are among the smallest particles. So we must be content and there is nothing that we can do. Okay, so this shows that when we consider not macroscopic objects such that the perturbations can be neglected, but when we consider microscopic objects, okay, since this microscopic object is what we have at our disposal to perform the experiments, then the perturbation induced by a measurement is something that cannot be avoided and cannot be neglected anymore. So instead of being just a nuisance that we can avoid easily by neglecting it, the perturbation during a measurement becomes essential, something that cannot be disposed of. If we keep thinking, we may think of another possibility. And the possibility is measuring the dynamics of microscopic particles using, instead of other particles, using light. So we may think of addressing photons against material particles in order to measure their positions, essentially. And maybe this is a way out, okay? For instance, when you watch on TV the race of Formula One and you see that some car is going 300 kilometers per hour, very likely they're using a laser to measure the speed of the car from the side of the track, okay? So we can think of doing the same thing, measuring the position of the electrons using light, maybe monochromatic light, okay? And this is in principle feasible because you remember, if you think of light as a collection of photons, so if you consider monochromatic light, you have photons all of the same frequency. Their energy is h-ni, okay? So and the momentum is, as you remember, h over lambda. Okay. So you may think of considering photons whose wavelength, sorry, whose frequency is very small, so that the energy of the photons is very small. The wavelength is very large, so the momentum is also very small. And in principle, you can decrease the frequency of the radiation as much as you please, so that eventually the momentum of the photons is so small that the impact on the measurement becomes negligible. It is sufficient that the momentum of the photons is much, much smaller than the momentum of the electron, and you again are in the position of neglecting the perturbation, as we did when considering the buzz against the tennis ball. This is in principle doable, but there is a drawback, and the drawback is the following, that if you decrease the frequency, you increase the wavelength. And the resolution of a measurement made with optical equipments depends on the wavelength, okay? You cannot have a resolution better than the wavelength, okay? So if you decrease the frequency and you increase the wavelength, the latter may become so large that the electron can be anywhere within a wavelength, okay? So you grossly mistake the position of the electron. You do not perturb the trajectory of the electron, not that much. But you mistake grossly the position. So if you want to measure the velocity, then you cannot measure anything, because if you have two positions that are quite long, you also grossly mistake the velocity, okay? So you see again that position and momentum in some sense are dual. If you do not perturb momentum, you do not get very well the position. If you want to obtain a careful measurement of position, then you must use, if you adopt an optical measurement, a very short wavelength, short enough to be as big as an electron in some sense. But in doing that, you must select a frequency that is very high. And a very high frequency means high energy, high momentum, high perturbation on the motion of the electron. So you are back in the situation of the lower part of this page. Again, we see that the operation of measuring introduce an essential perturbation on the object that is being measured, okay? One last objection is possible, but is it really true that in order to measure something, we must interfere or interact with the object? Let's take a situation that looks easy, okay? You want to measure the trajectory of the moon. You know that when man landed on the moon about 50 years ago, they placed a mirror on the moon so that, exploiting the mirror, later they could measure the distance between Earth and moon by shooting a laser beam from Earth to the mirror and measuring the time that it took for the light to travel to the moon and come back. Okay. Is this measurement perturbing the moon? Well, yes, because the light of the laser exerts a pressure. Okay, so when the light arrives on the mirror, it exerts some pressure on the mirror, not that much, but some finite pressure. And through the mirror, this pressure goes into the moon, okay? Is applied to the moon as a whole. So the moon will bounce a little bit back because of this pressure. Of course, this is so small that nobody cares, okay? So again, we have an example of measurement in which the perturbation is negligible. But you may still say, if I just stay on Earth and I look at the moon, okay, without any laser, any nothing, okay? If I just look at the moon, do I perturb the moon? Can just I watch the moon without doing anything through my eyes or through a telescope? Okay, this should be a measurement without any perturbation. Even in this case, there is some perturbation because in the environment there are photons anyhow, okay? And these photons go into the mirror that is at the bottom of the telescope, and they are reflected to the moon, okay? So if you block the lid of the telescope or open the lid of the telescope, this reflection will be different. Of course, it will be very small, so completely negligible, but it will, in principle, it will exist. And even if you look at the moon, if you close your eyes, your eyelids will reflect differently with respect to the case in which you keep your eyes open, okay? And still there will be just a few photons that will behave differently. So it's impossible to measure something without interacting with that something. So we are back to the issue that we must abandon the idea that is so convenient in classical mechanics that the motion of particles can be described by differential equations that provide us with the full information at each time of position, velocity, energy, and all dynamics quantities of these particles. And we must be content with a smaller amount of information that is associated to the statistical distribution of the particles, if we are considering many particles, or to the probability of localizing a particle in some region of space. And you remember that in this respect, we have already introduced the wave function that depends on position and time, and we have associated a meaning, a physical meaning to the wave function. And this physical meaning is that the square modulus of the wave function integrated over the volume provides the probability to find a particle in that volume, provided the wave function can be normalized, okay? In the few cases in which the wave function cannot be normalized, we have to use some extra care in order to define the ratio of probabilities. Then we also, at some point, we decided to split the problem by considering for the moment only the situation in which the forces acting on the particle are conservative, okay? So that we have, for the moment, to deal with forces that are derivable from a potential energy. Okay. And since for a conservative case the total energy is conserved, we can say that if the total energy of the particle is given, then you remember the angular frequency omega to be associated with the wave function described in the particle is also given. It is equal to the energy divided by the reduced Planck constant. And in the conservative case, we acknowledge the fact that the wave function can be split into the product of the space part that is still to be found and the time part that is the exponential of minus j omega t. So we are now left with the problem dealing with the conservative situation of finding the space part of the wave function. Qualitatively, we may state that this function will be the result of the solution of a differential equation, and that since the function contains only the space coordinate, okay, it should be a differential equation in the space coordinate, okay? It is possible to derive such an equation. This equation is, as you may anticipate, is the Schrödinger equation independent of time, okay? There are several methods to deduce the form of the Schrödinger equation independent of time. We shall skip all these derivations. So I'm going now directly to show you the form of the equation. So let me rotate the screen. Okay. The equation that you see on top is the Schrödinger equation independent of time, whose unknown is W, and as you remember is the space part of the wave function. So the Schrödinger equation independent on time has, on the left-hand side, has one term that is proportional to the Laplacian of W. And there is a coefficient that is minus the square of the reduced Planck constant divided by 2 times the mass of the particle. This is the non-relativistic form. We will not deal anymore with relativity, so everything will be non-relativistic from now on. So this is the non-relativistic form, and m is the rest mass of the particle. Then, still at the left-hand side, V is the potential energy of the particle. So V is the function such that minus the gradient of V is the force acting on the particle. So V depends on position in general. On the right-hand side, E is the total energy of the particle, and E is a constant, okay? This equation, I don't know how much you have seen of calculus. if V, the potential energy, was a constant, then this would be the Helmholtz equation. Okay, so this is a more general equation in which the coefficient V depends on position. So you see immediately that this equation is linear in the unknown W. And also it is homogeneous. Okay. It is an equation of the second order because the Laplacian is a linear second order differential operator. And as we shall see in the examples, the boundary conditions of this equation are also homogeneous. Okay. So this equation is a homogeneous equation whose boundary conditions are also homogeneous. Okay. So this is sufficient to say that the solution of the equation is defined apart from a multiplicative constant. Okay. It may happen, and it is easy to find examples of this type, that some solutions of this equation diverge. Okay, if we take easy examples, we shall immediately see that if you go to infinity, there could be solutions that diverge. Okay. If it happens that you find solutions that diverge, they cannot be accepted on physical grounds. So they do exist for mathematical reasons, but they are not acceptable for physical reasons. So diverging solutions must immediately be discarded. Okay. Non-diverging solutions may be normalizable or not. So you remember, normalization implies that the square modulus of the complete wave function psi, when integrated over infinity, gives you a finite result. Okay. On the other hand, the full wave function psi has a time coefficient that is the exponential of j omega t. So the square modulus of this part is 1. Okay. So for a monochromatic wave function in which only one multiplicative coefficient exponential of minus j omega t appears, the square modulus of the wave function is equal to the square modulus of the space part W. Okay, so for the normalization, it is sufficient that we consider the integral of the square modulus of W over the full space. Okay, so if this integral does not diverge, so if it gives some finite positive number, then the wave function can be normalized. So we can rescale the wave function in order to obtain that this integral is equal to 1. And this is possible, as we anticipated, because the equation is homogeneous and the boundary conditions also are homogeneous. So the solution in any case is defined apart from a multiplicative constant. If instead the square modulus of W after integration over infinity does not converge, there is nothing that we can do. There is no normalization possible, of course. A typical example is the space part of the wave function associated to the free particle. You remember it is some constant a times exponential of jk dot r. What about the continuity of the wave function? Of course, it is continuous in space because since W fulfills a second order differential equation, not only it must be derivable twice. W must be derivable twice. So of course it must be continuous, and also the derivatives are continuous because we need the second derivatives, okay? So W is continuous and its first derivatives are continuous. What about the second derivatives? Well, it depends, because if you look at the equation, you see that if you bring the term V times W to the right, okay, you are left on the left with the second derivatives, okay? So the second derivatives are continuous or not, depending on what the term EW minus VW is doing. So E is a constant. W is continuous, as we know. But V, the potential energy, may be continuous or not. If you consider, for instance, a potential energy that has the form of a step or of a barrier, it is discontinuous. So in those cases, the second derivative is also discontinuous, but there is no problem in it. We just take it, okay? For this equation, it is convenient to use a more compact notation. So we introduce an operator, and this operator is defined as, you see here, minus the reduced Planck constant squared divided by 2m times the Laplacian plus v. Of course, the Laplacian is an operator. V is a function. V is a function, but you may think of it as a multiplicative operator. If you look at the equation, the Laplacian operates on W because it calculates the second derivatives. V operates on W just by multiplying W. Okay, so you can think of V as a multiplicative operator, and then you extract W and introduce this operator that is indicated with the symbol H and is called the Hamiltonian operator. So when you define the Hamiltonian operator, you can write the time-independent Schrödinger equation in a more compact form that is H operating on W equal to E times W plus the boundary condition. The symbol of BC means boundary conditions, okay? Think for a moment that the Hamiltonian is a matrix, not an operator, and that W is a vector, okay? You see that that would be an eigenvalue equation of algebra, okay? In the continuous case, an operator operating on a function equal to a constant times the same function is still an eigenvalue equation, okay? So actually the Schrödinger equation is an eigenvalue equation in which the energy is the eigenvalue and the solution W is the eigenfunction, okay? Obviously, the Hamiltonian operator is linear because the original equation is linear, okay? So linearity means that if we apply H, as you may see in the second dot of this page, if you apply H to a linear combination of two functions, C1 W1 plus C2 W2, what you obtain is the linear combination of C1 times the Hamiltonian onto W1 plus C2, the Hamiltonian onto W2, okay? There is another interesting observation that the Schrödinger equation has a formal similarity with the classical expression of the total energy of the particle in a conservative field, okay? If you take a classical dynamics of a particle of the conservative type, so that you have a potential energy V, you remember that in this case, V is the potential energy and it depends only on the components of position of the particle. V depends on R, okay? In turn, the kinetic energy, T, is the square of momentum divided by 2m. So the kinetic energy depends only on the coordinates of momentum. The sum T plus V is a function that you may remember it is called the classical Hamiltonian function, H. This classical Hamiltonian function being the sum of T that depends on P and V that depends on R or Q. Q is a more general symbol for the space coordinates, okay? Q is like R. Then the Hamiltonian function is a function of P and Q, or if you wish, of P and R, okay? But being the sum of kinetic plus potential energy, the classical Hamiltonian is also a constant of motion. So H is equal to a constant that we call E, okay? And if you look at the Schrödinger equation above, we have H considered as an operator acting on W is equal to E acting on W. If for a second you cancel W, of course it is not legitimate, but think for a moment of eliminating W from the Schrödinger equation, you have H equal to E, which is formally similar to the classical counterpart Hamiltonian function H equal to total energy E, okay? But we can do more, because if we compare the form of the Hamiltonian operator minus h bar square over 2m Laplacian plus v with the classical total energy T plus V, we observe that V is the same. V is not changed. V is just the same in the classical description and in the quantum description. Instead, the kinetic part in the classical case is, as you see here, p squared over 2m. And in the quantum case, it is a block that we can again call T with a fancy T, equal to minus h bar squared over 2m Laplacian, where 2m is the same 2m that appears in the classical kinetic energy. So we are led to think that we go from the classical kinetic expression, the classical expression of the kinetic energy to the quantum expression of the kinetic part of the Hamiltonian by replacing p squared with minus h bar squared Laplacian. Okay, so this is written in a larger form on this line. Okay, so the formal correspondence between the classical Hamiltonian function and the Hamiltonian operator is to be seen in the kinetic part. And the kinetic part of the classical one transforms into the kinetic part of the quantum operator by this replacement. Okay? The square modulus of momentum that can be written as a sum of the squares of the individual components divided by 2m becomes minus h bar square over 2m Laplacian. Okay, if we consider this component by component, it is like taking each component of the classical momentum pi and replacing this classical component with a quantum operator that we call pi hat. We call this the momentum operator associated to the ith component of the classical momentum. And this momentum operator is defined as minus j h bar times the derivative with respect to the position component of the same index I. Okay, why? Because if you need the square in order to form the kinetic energy. If you take the square of pi and you think of the operator instead, the square of an operator is like applying the operator 2 times, one after the other, okay? So if you apply the operator 2 times, you have the derivative 2 times. That is the second derivative with respect to xi squared. Then h times another h gives you h squared, h bar squared, and minus j times minus j gives you minus 1, whence the minus that you find here. So this is the formal way to transform the classical Hamiltonian function into the quantum operator that is the Hamiltonian for our particle. Okay, this can also be generalized, that we shall see with some examples. Let's see what comes next. No, it's too long, so we stop here and we shall continue in about 10 minutes. Okay, so let's continue the analysis of the time-independent Schrödinger equation. And we ask ourselves this question. When you consider the classical case, still in the conservative situation, you remember that the total energy E in a classical situation can never be smaller than the potential energy, because if that happens, then the kinetic energy must be negative, and this is impossible because the kinetic energy is a square, okay? When we transform the classical expression of the conservation of energy into the Schrödinger equation independent of time, what happens of this property that the total energy cannot be smaller than the kinetic energy? Can we demonstrate something similar? We can do it, and it is instructive because it shows immediately one of the possible tricks of the calculations involved in quantum mechanics, okay? So we take the Schrödinger equation, and for the moment, we assume that the solution of it is complex, okay? Sometimes it is convenient, as we mentioned, to use complex functions instead of real functions, because in any case, the physical information about the localization of the particle is associated to the square modulus, and the square modulus in any case is a real quantity. So if you take the Schrödinger equation that you see on the screen, you can multiply it on the left by the conjugate of W. I tell you the story, and then we will go into the details with the calculation. We multiply it on the left. On the left means that the multiplication, the multiplying factor, that is the conjugate of W, is placed on the left of the operator. Because if you put it on the right of the operator, then the operator would also operate on the new factor, and you don't want it, okay? So you place it on the left. After that, you integrate both sides over the full space, okay? So what you obtain is this. Oh, before doing that, you bring the potential energy to the right-hand side. So you rewrite the equation in the form that is written in the first line, minus h bar squared over 2m Laplacian of W equal to E minus V times W. Then you multiply both sides by W, and then you integrate over the volume. So obviously, in the right-hand side, when you multiply by the conjugate of W, what you get is W modulus square, okay? Because you have W star, that is the conjugate, times W. On the left-hand side, you have to introduce some form of manipulation, because you have the conjugate of W times the Laplacian, okay? You can exploit a vectorial identity, that is that the product W star times the Laplacian can be written as the divergence of W star times the gradient of W minus the square modulus of the gradient of W. Actually, for this, you should start with the divergence, calculate the result, and then you bring the square modulus of the gradient to the right, okay? So you replace this expression into the integral on the left, and then you split the integral. So what you get is that 2m over h bar squared times the integral of E minus V times the square modulus of W integrated over some volume is equal to, then you have the gradient of W squared integrated over the same volume, and then you have the integral over the same volume of the divergence. But you remember that the integral of the divergence over a volume by the Gauss theorem can be manipulated and becomes the integral over the surface of the volume of the normal derivative of the argument of the divergence. Okay, so the normal derivative is, of course, W star times dW d ni. Ni is the unit vector normal to the boundary and pointing in the outer direction. And delta tau is the boundary of tau, okay? Now you let tau go to infinity, okay? And you assume that this function W is normalizable, okay? So in this case, if the function is normalizable, necessarily it goes to zero when you extend the boundary to infinity. If it does not go to zero, it cannot be normalizable, okay? Because the integral would diverge, okay? So W must go to zero at infinity. But if W goes to zero at infinity, also W star, that is the conjugate, goes to zero at infinity. So the last integral, the integral that is carried out over the boundary, vanishes. Instead, the gradient of W inside the volume cannot be zero, because W is, by hypothesis, one of the possible eigenfunctions of the equation, and the eigenfunctions are non-zero, okay? So we discard the trivial solution of the equation that is W identically equal to zero, and we seek for the solutions that are non-zero. If W is non-zero inside the volume, but it becomes zero at the boundary, then the gradient must be different from zero inside, okay, in order to make this possible. So the gradient is strictly different from zero, so the square modulus of the the square modulus, yes, of the gradient is strictly positive. That means that the integral of gradient of W squared is strictly positive. That means that the integral on the left is also strictly positive. So we eliminate the constants and we find that the integral of E minus V times the square modulus of W integrated over tau is strictly positive, okay? But this means that if you split the integral into two blocks, one block contains the constant E, and the other block is the integral of V times square modulus of W, you obtain the relation that is visible on the right of the arrow. That is, the total energy is strictly larger than the integral of V weighted by the square of W normalized by W. Okay, obviously, the integral in the numerator is larger or equal to the integral that you obtain by replacing V with the minimum of V. But if you do so, you can extract the minimum of V from the integral, the other part cancels the denominator, and so we arrive at the conclusion that the total energy, if the wave function is normalizable, is strictly larger than the minimum of the potential energy. So the quantum mechanical situation has a constraint that is stricter, okay? In the classical case, you may have that the total energy may also be exactly equal to the potential energy. In that case, the velocity is zero because the kinetic energy is zero. In the quantum case, if the wave function is normalizable, the energy, the total energy, is strictly larger than the minimum of the potential energy, cannot be equal, okay? If instead the wave function is not normalizable, and the typical example is that of the free particle, then you cannot exploit anymore the property of W to vanish at the boundary. W does not vanish at the boundary when it is non-normalizable. So in this case, it may happen that E becomes equal to the minimum of the potential energy, but in any case, E cannot be smaller than the minimum, okay? So the situation in this case is identical to that of the classical case, okay? The second part that E must be larger or equal than the minimum of the potential energy is easily proven in the case of the free particle, so I do not repeat the calculation. The calculation is in the last line of this page. Now, let's see some simple example, okay? And of course, the simplest example is that of a free particle. So we can put the potential energy to a constant, and we may choose this constant at will. So we put V equal to 0. And the Schrödinger equation becomes Laplacian of W proportional to W, as you can see in the second line of the page. And this equation is separable because the operator is the sum of three terms that depend only on the derivative on x, y, or z. And W can be expressed as the product of three functions that depend on x, y, and z. So it is separable, and this problem of separation will be considered later. So for the moment, we don't talk about separation, okay? So it is sufficient to know that we can solve this equation in one dimension only, okay? And what we obtain is exactly what we would obtain by separation. So if we consider the equation in one dimension only, the Laplacian becomes the second derivative with respect to x. And we see immediately that since V in this case is equal to 0, the total energy cannot be smaller than V. We have just proved that. In the case of a free particle, the minimum of E is equal to the minimum of V, but it cannot be smaller. Since V is 0, E cannot be negative, okay? If we try to solve this equation by considering E negative, we could immediately find that the solution would be a combination of real exponentials, and these real exponentials would diverge because e to the x diverges when x becomes infinitely large, okay? But the other solution, e to the minus x, would also diverge for x going to minus infinity, okay? So no solution would be acceptable. So we must discard the possibility that e is negative. So we must consider two possibilities, E equal to 0 or E larger than 0. E equal to 0 is immediately found because if you let E equal to 0, you find the second derivative of W equal to 0. That makes W equal to a linear function of X. So in that case, W is A1X plus A2. But obviously, this solution diverges because when you let x go to infinity or minus infinity, W would diverge. So in order to prevent the divergence, we must set A1 to 0. So the conclusion is, in the case E equal to 0, W is just a constant, okay? Instead, the other possibility is that E is larger than 0, so we have that the second derivative is equal to minus a positive quantity, that is 2m E over h bar squared times the unknown function W itself. And you remember very well that the solution to this equation is a combination of exponentials with imaginary exponents. So the solution is W equal to some constant C1 times exponential of j kx. K is found from the equation. It is the square root of the coefficient. So it is the square root of 2m E divided by h bar squared. Okay. And the other independent solution is C2, that is another constant, times the exponential of minus jkx. By the way, you remember that in the case of a free particle, the total energy is equal to the kinetic energy. So E is T, and T is P squared over 2m. So actually K is equal to the modulus of momentum over h bar, as we know very well, okay, from the de Broglie hypothesis for the free particle, okay? So in conclusion, for the free particle, the situation is quite easy. We have found that the space part of the wave function is a combination of the two exponentials in which the constant C1 and C2 are undetermined. And we don't have any method for determining them because there are no boundary conditions in this equation, okay? W does not go to 0 at infinity. It's just the same everywhere, okay? So it is non-normalizable, and we do not have any possibility to find the two constants. But we can reconstruct the full time-dependent wave function, because you remember when you have a conservative case with a given total energy E, then the angular frequency that must be used in the time factor of the wave function is the exponential of minus j omega t, with omega equal to the total energy E divided by h bar. So we take the solution W and we multiply it by the time factor, okay? And when you do that, you have that psi is equal to the sum of two blocks. One block is C1 exponential of j kx minus omega t. And what is this? This is a planar monochromatic wave with wave vector k and angular frequency omega. And this planar and monochromatic wave propagates along the x-axis in the positive direction of the x-axis. Positive direction because the sign of k and omega are opposite in the exponent, okay? K has a plus and omega has a minus. The other term is C2 exponential of minus j kx plus omega t. So this is another planar and monochromatic wave that propagates along the x-axis, but in the backward direction, because the sign of k and omega are equal to each other. Conclusion: the general solution of the problem for the free particle, we could repeat it in 3 dimensions, but it would be just the same, okay? Is that the wave function is the superposition of two planar and monochromatic waves. One wave propagates in the positive direction of the axis and the other one propagates in the negative direction of the axis, okay? The total energy can be any positive number, okay? We leave apart the case equal to 0 that was discussed earlier, okay? So the total energy is some non-negative number, okay? And could be any number, so there is no constraint on the total energy apart the fact that it cannot be negative. So we have full knowledge of energy and also full knowledge of the modulus of momentum, that is h bar times k, okay? Of course, we have no information about the position of the particle, because those two terms, the exponential, if we take a picture of the function at some t, we see that it is a combination of two exponentials with respect to x, and they are non-zero everywhere along the axis, okay? So the particle has a non-zero probability of being found anywhere along the axis, so no information about position, but also no information about the direction of momentum. Why? Because we started from an equation in which the only parameter given was the total energy. And in this case, since we have a free particle, the total energy is purely kinetic. And you remember, if you give an energy, you also find the modulus of momentum, but not the direction of momentum. It could be positive or negative. Okay, so there is no information in the equation about the direction of momentum. If you take a measurement at some instant of time, then you can, from the measurement, deduce the direction of momentum. Okay, but for that you need a measurement. Okay, so if you take a measurement on this wave function, you find either the case in which the particle is moving along the positive direction of the axis, or the other possibility, you find that the particle moves along the negative direction of the x-axis. Of course, the particle cannot simultaneously move along both directions, okay? So the description of the wave function gives you the two possibilities because it gives you a probabilistic picture, okay? So given the total energy, the particle may move in the positive or negative direction of the x-axis. That means that the two coefficients, C1 and C2, may be non-zero both. If you measure, then you find that either the particle is going to the positive direction, so that C1 is non-zero and C2 is zero, when you have finished the measurement, or conversely, you may find that the particle is moving into the negative direction of the axis. So what you do, because of the measurement, you find that C1 becomes zero and C2 is non-zero. Okay, but this can be ascertained only by a measurement. Let's change slightly the situation. So let's consider the situation of so-called the problem of a particle in a box. What is a particle in a box? It is a particle that is such that there is an interval that we can consider between x equal to 0 to x equal to some value a. Okay, so there is a finite interval of the x-axis in which the potential energy is 0. And then at x equal to 0 and at x equal to a, the potential energy becomes finite with a discontinuity. I'm going on with the pages and I'll come back just because I want to find a figure that shows the situation. There it is. So the box is something similar to the thing that is called well in this figure, okay? The only difference is that between 0 at some value that here it is called S, in the other page it was called A, the potential energy is zero, and then it is positive on the right and on the left. So it is the same figure as you can see here, only shifted upwards, okay, by the amount V0, okay? So this is called well. The solution in the well is not so easy, but it is made much easier if we assume that the two sides of the well go up to infinity. So the potential energy on the two sides becomes infinitely large, and in conclusion, this makes impossible for the particle to, for the wave function of the particle to be different from zero on the left of the origin or on the right of A. This is not obvious. This is not obvious. What people should do is calculating the solution in a finite well and then taking the limit afterwards, okay? So we assume that we have done it, okay? So in this case, we know a priori that the wave function will be identically equal to zero outside the interval 0a, okay? So the equation now takes the form in one dimension, second derivative of w with respect to x equal to minus 2m over h bar squared, e minus v. V is 0 inside the interval 0 to a, and v becomes infinitely large outside this interval, okay? For this reason, since we know that w is identically equal to 0 outside the interval, we can calculate w only inside the integral, okay? So this seems to bring the problem, to make the problem identical to the problem of the free particle, because we solve the Schrödinger equation only in the interval in which the potential energy is equal to 0, which corresponds to the case of a free particle. But there is a fundamental difference, and the fundamental difference is that the wave function vanishes outside the interval between 0 and a. But you remember the wave function is continuous, so it must be also equal to 0 at the boundary. So we have the information, the additional information that was not available, of course, for the free particle, that V of W and V of A is 0. So we do have two boundary conditions for this second order differential equation, in contrast to the case of a real free particle case in which there were no boundary conditions, okay? Since the wave function is non-zero only in a finite volume or interval in this case, we may expect that we shall be able to normalize the wave function, because we expect that the integral of the wave function over a finite interval is finite, okay? So let's proceed now to the solution. We solve only in the interval between 0 and a, in which the potential energy is 0. So we obtain exactly the same solution as for the free particle. So the form of the solution is identical. W is C1 exponential of jkx plus C2 exponential of minus jkx, and the expression of k is just the same as before. It's square root of 2me over h bar squared, okay? But now, oh, by the way, when we start from the well of finite depth, and then we let V0 go to infinity, the well becomes a box. So a box is a well whose two sides are infinitely high. So what we do now is we impose the boundary condition. So the first boundary condition is at x equal to 0. If we let w at 0 being equal to 0, we obtain that C1 plus C2 is 0. Okay, so actually the two constants are not independent in this example. C2 is equal to minus C1, so this expression becomes 2 times j C1 sine of kx, okay, because it is exponential of j minus exponential of minus j, so it is twice the sine of kx. Then we impose the other boundary condition, that is v at a equal to 0. So if we place x equal to a, we have that sine of ka must be 0. And for this, it is necessary that ka is an integer number times pi, okay? So in this case, we have the quantization because the solution of the Schrödinger equation for the box that fulfills the boundary condition is such that we have a relation involving an integer, okay? What is the outcome of this integer? Well, a, of course, is given because it is the width of the box. Pi is given, so this is the definition of the possible k. The conclusion is that, in contrast to the case of the free particle, in which any non-negative value of E was allowed, so that also any value of K was possible, non-negative, okay? In this case, the possible values of K that are allowed are those that fulfill this relation. So K is quantized, and as a consequence, the energy that is uniquely related to K is also quantized. So the energy becomes E sub n, and if you replace K from here, K, as you see from this equation, is n pi over A with n some integer, okay? So the eigenvalue of the equation is this. It's proportional to n squared. And then, similarly, if you replace the same expression of k here in the sign of kx, you obtain the form of the eigenfunction. Okay, so the eigenvalue is E sub n. The eigenfunction is W sub n, and its form is here. Still, we miss this coefficient C1, okay? This coefficient C1 did not come out from the boundary condition. It will come out from the normalization. So for the moment, C1 is some non-zero number, okay? That may be complex. Let's now see what are the possible values of the index, because here we have any integer, okay? Of course, we must exclude the case in which n is equal to 0, because in that case, the eigenfunction would be identically 0, but the eigenfunction must be non-zero. Okay, when you have an eigenvalue problem, you seek for the functions that solve the problem and are non-trivial, that is non-identically 0. Okay, so we exclude n equal to 0. Also, we exclude the negative indices because the physical information related to the position of the electron is related to the square modulus of W, and of course the square modulus of W and the square modulus of minus W are the same, because when you change the sign of n, the sign function changes sign, but the square modulus does not. Okay, so the numbers n that we should select are 1, 2, whatever, up to infinity. There is a figure here showing the eigenfunctions of the particle. I'll zoom out. So the function corresponding to n equal to 1 is this, with only one maximum here up to here. The one that corresponds to n equal to 2 is this one, having 1 0 in the middle and 2 zeros at the boundary. The one with the 3 is this one. You need is the thick one, this one. 1 0 here, another 0 here, and 2 zeros at the boundary, and finally this one is with n equal to 3. You may observe a feature of these functions. They have a discontinuity in the first derivative at the boundaries, because all these functions arrive at the boundaries with a non-zero derivative, but then, if you remember, when you exit the box, they are identically equal to 0, here and there. So in this case, there is a discontinuity of the first derivative, but this is no surprise, because the potential energy has a second order discontinuity, because we let it go to infinity. Okay, so this is a very special case. How do we interpret this, the solution that we have just found? Well, the interpretation is easy. Since W is identically 0 outside the box, the probability to find the particle outside the box is 0. So the particle can never be found outside the box, can be found only inside the box, okay? In which the probability to find it is non-zero, okay? Then the probability depends on the eigenstate, so it depends on the value of the energy. So you fix the index, then you determine the energy, and then you calculate with the same index the eigenfunction, and then you take the square modulus of the eigenfunction for the probability density, okay? We are left with the problem of this constant C1, okay? That is some constant, okay? But now we can also try to complete the job by normalizing the wave function. So what we do is we take the square modulus over the box, because outside we know that the function is identically 0. useless to try to do it. So we take the square of this function, and then we integrate it over the box. So let me zoom in. We extract all constants. We are left with the integral of sine squared. We renormalized the integration variable. Then we integrate by parts. And what we find is that the integral is equal to n pi over 2. But this n pi kills the n pi in the denominator. And finally, we impose that the full integral is equal to 1 in order to achieve the normalization. When we do so, we have an expression involving the last constant, C1, when we impose that it is equal to 1, that the integral is equal to 1, we find that 4 times the square modulus of C1 is 2 over A. Take the square root, we select this, and we find that the eigenfunctions of the box are, the normalized eigenfunction of the box are square root of 2 over A times sine of n pi over A x. It is worth making another observation. When you prescribe the index, you remember that index n of this problem goes from 1 to infinity. Okay, when you fix n, you find one energy. Of course, you find one and only one energy that has this expression. And using the same n, you find one and only one eigenfunction. So in this problem, there is a one-to-one correspondence of the eigenvalue with the eigenfunction. For each eigenvalue, there is one and only one eigenfunction. This is not always the case. There are problems in which for one eigenvalue, you may find more than one eigenfunction, okay? In this case, you have only one-to-one correspondence, so the eigenvalue is called simple, because there is only one eigenfunction corresponding to it, okay? So you see that considering essentially the same problem, a particle in one dimension with the zero potential energy yields to completely different situations if you consider a free particle or a particle in a box. For the free particle, the energy can take any positive value. There is no index, so the energy can be chosen over a continuous domain, E larger or equal than 0 with no constraints. Instead, when you consider the particle in the box, the energy is quantized. So it is the boundary condition that provide the quantization. Also, if you go back to the case of the free particle, you have that given the energy, that is any non-negative number, you find k, assume that E is positive, so neglect the k is equal to 0, okay? You find some non-zero value of k that is strictly positive, and you find two possible solutions that are linearly independent from each other. One is exponential of j kx, and the other is exponential of minus j kx. So in this case, you have that the eigenvalue is continuous. There is no index, okay? But there are two eigenfunctions that are linearly independent from each other corresponding to the same energy. So for the free particle, the eigenvalue is not simple. We say it is degenerate of order 2 because there are two linearly independent eigenfunctions corresponding to the same eigenvalue. Okay, so I think this is it for the free particle and also for the box. Let me check. Yes, so we just stop here and we shall continue tomorrow. Thank you very much.